This lecture introduces elementary matrices. So when we perform exactly one elementary row operation on an identity matrix I, then the resulting matrix is one of the elementary matrices. Okay. So for an example, if I'm consider using an identity matrix 2 by 2, so it's going to be 1, 0, 0, 1, right? Okay. Then because we have three different row operations, that means we have three different types of elementary matrices. Type 1 is a matrix obtained by interchanging two rows of an matrix. So I would call it I1, right? So if you have as an identity matrix, and I1 is just, let's say E1. E, the first type of elementary matrix is a resulting matrix from interchanging two rows of I. So if I interchange row 1 and row 2, then I will get an E1, right, from this identity matrix. And this E1 here will be 0, 1, 1, 0. Okay. Again, if you interchange two rows of an identity matrix, the resulting matrix will be an elementary matrix of type 1. How about type 2? Type 2 is an elementary matrix when you multiply a row of an identity matrix by a non-zero constant. So let's say I take row 2, and then I multiply 2 row 2, okay, from this identity matrix. And then to get a type 2 elementary matrix. And type 2 elementary matrix will be, because I'm multiplying row 2 by 2, then row 1 stay the same. Since this row 1 stay the same, and row 2 will be 0 times 2 is 0, and 1 times 2 is 2. Okay. Again, this is my row operations. This is my identity matrix, and this is my elementary matrices according to these row operations. How about type 3? Type 3 is a matrix obtained from, again, the identity matrix, but by adding a multiple of one row to another row. Let's say I wanna take row 3, I take row 1, to row 1 plus row 3. Okay, so that this is my row operations. I replace row 3 by row 3 plus 2 row 1. Okay, and then I will add a elementary matrix of type 3. It will be, why is row 3? I only have 2 rows, so it should be row 2. I want to say row 2. And 2 row 1 plus row 2. Then I have an elementary matrix of type 3. Row 1 will stay the same. Row 2 will be 2 row 1 times row 2. So you can see that 2 row 1 times row 2 will be 2 times 1 is 2 plus 0 is 2 here. And 2 times 0 is 0 plus 1 is 1. Okay, so here are here are 3 types of elementary matrices by applying elementary row operations onto an identity matrix. Okay, well, let's do a couple of examples. Well, let's consider two matrices. One is an arbitrary 3 by 3 matrix, right? Another one is E3, is an elementary matrix of type 3. Using this E3 here, I could guess that this is the resulting matrix of applying the third row operations on an identity matrix, 3 by 3 identity matrix. And from my guess, so row 2 and row 3 stay the same, row 1 change, and the way row 1 change is row 1 equals to 2 row 3 plus row 1. Do you agree? So if I take 2 row 3, so 2 times 0 plus 1 is 1, right? 2 times 0 plus 1 is 0. 2 times 2 plus 0 up here gonna be 2. So this is the row operations that I use on a 3 by 3 identity matrix to get this row elementary, to get this elementary matrix. That's what my observations, but the task that I'm asking to do is, if I take an arbitrary 3 by 3 matrix and I multiply E3 to A, what would I get? Okay, so if I call A by its entries, right, Aij, then I want to do a matrix multiplications. E3 1 0 2 0 1 0 0 0 1, and A will be just A11, A12, A13, A21, A22, A23, A31, A32, A33. Okay. Well, as you know, we know how to do matrix multiplications. We take row and we dot products to columns, right? To get the first row and first column entries of the product. So if I do this, it will be 1 A11 0 plus 0 A21 plus 2 A31. So the result will be A11 plus 2 A31. So this is the first entry. So if I take the first row and the second column, first row, second column, what would it be? First row and second column. So it's gonna be A12, 0 to A32. A12 plus 2A32. Okay. And then if I do it, the first row and the third column, I would have A13 plus 0 times A23 plus 2, A33. So I'm done with my first row of the product, E3A. Okay, and you can see that I take A11 plus A31, A12 plus A32, and so on and so forth. All right. So now I will go to the next row, second row, first column. And second row, first column, as you can see that you take this 0, 1, 0, and you dot with A11, A21, A31. The result is just A21. Okay. Similarly, the result is A22, A23. If you take the last row and you dot products with the column, you will see that the result will be A31, A32, and A33. Okay, so that's the first product. An elementary matrix E3 multiplied to A on the left side, right? Now, because we know that matrix multiplication is not commutative, that means E3A times A could be different compared to A times E3. Let's try it. Now I have A is A11, A12, A13, A21, A22, A23, A31, A32, A33. Okay, you multiply to E3, and we know that E3 is 1 0 2 0 1 0 0 0 1. And the result is, as we know how to do matrix multiplications, I will again take row, column. In this case, A1, 1 will stay, row, column, A1, 2, row, columns here. You will have 2A11 plus A13. Okay, so that's the first row. How about the second row? You will have second row, first column, again, A21, second one, A22, and then the last column, you will have 2A21 plus A23. Okay, last row, you will have A31, A32, and the last one is 2A31 plus A33. Okay, now we can see that these two matrices here are not the same. How different they are. Well, if you multiply, as you see that if you multiply a matrix by an elementary matrix on the left, what you did was you transforming the rows of the original matrix A, right? So what you did was you transform row 1 by row 1 plus 2 row 3, which is what we did. Row 1 equals to 2 row 3 plus row 1. Okay. But if you multiply a matrix by an elementary matrix on the right of that matrix here, then the result that you get is you changing the column of the matrix, not the row. And how do you change the column of the matrix? So if you look at the elementary matrix here, look at this matrix from the column perspective, right? So you can see the first column stay the same, the second column stay the same, but the third column equals to 2 of the column 1, so column 3. All right, column 3 is equals to column 3 plus 2 column 1. Okay, so this is what you did here, right? Column 3 equals to 2 column 1 plus column 3. And as a result, A times E3, when you take A times E3, you're changing column 3 by taking 2 column 1 plus column 3. So this is the difference when you multiply a matrix to an elementary matrix. So if you multiply an elementary matrix to on the left of a matrix, that's when you change the rows of the original matrix. But if you multiply an elementary matrix to the right of the original matrix, that is when you're changing the columns of the original matrix. Keep in mind. All right. Now, we have a theorem saying that if E is an elementary matrix, then E is non-singular. Okay, and then since E is non-singular, then E inverse exists and unique, and also E inverse is an elementary matrix of the same type. All right. So again, E, you have an elementary matrix, is non-singular, is inverse exists, and is inverse is also an elementary matrix of the same type, type 1, type 2, and type 3. Then to row equivalent matrices. So we can define the two matrices or row equivalents if there exists a finite sequence E1, E2 to EK of elementary matrices such that if you multiply this elementary matrix to matrix A, you get matrix B. And again, because you're talking about row equivalent matrices, you want to multiply these matrices, these elementary matrices on the left of A to get B. All right. So again, keep in mind, one elementary matrix represents for one row operations. So the fact that you have a sequence of elementary matrix, or you have a product of the sequence of elementary matrix multiply by a matrix A on the left, that means you can go from A to B by performing k number of row operations to go from A to B. So that's how you define if the two matrices are row equivalents. If they are equivalent, that means there exists a finite sequence of elementary matrices multiplied to a matrix on the left to get to another matrix. Well, let's look at this example 10 and 11. So for 10, for each of the following pair of matrices, phi an elementary matrix E such that E times A equals to B. Again, you want to find E, so then when you multiply E on the left side of A, you get B. That means you changing one of the rows of A by using this E, this elementary matrix E. That means we have to look at rows of A and B, right? So from A to B, comparing A and B, row 1 and row 2 are the same. Row 2 and row 3 here, so see, are switch, right? So row 2 in A is row 3 in B, and row 3 in A is row 2 in B. That means from A to B, the row operation that you have done on A to go to B is you take row 2 and you interchange row 3. Okay, so what is the E? So E, in order to come up with E, you have to start with an identity matrix. So an identity matrix in a 3 by 3 identity matrix is, let's say, I equals to 1 0 0 0 1 0 0 0 1. Okay. Start with I and you interchange row 2 and row 3 to get E. So row 1 stay the same, row 2 will become row 3, and row 3 will become row 2. So this is the elementary matrix E that you want to, you're looking for. So then E times A equals to B. All right, how about the second one? So again, we look at rows. So the first rows are the same, the second row the same, but the third rows are different here. How can you go from this row to this row using one of the row operations? So you can see the 0, that means the second row. There's two possible ways. You can take row 2, row 3 equals to row 1 plus 2 row 3. 2 is 0. How about -2 plus 2 times 3 is 6. So -2 plus 6 is -4. No, it's 3. It's not. It's 3. So it doesn't work. This doesn't work. If this doesn't work, then you want to look for, okay, so another option is you take row 3 plus 2 row 2, right? Because -2 plus 2 times 1 is -2 plus 2 is 0. Then, well, then you can check. So the first entry works because -2 plus 2 times 1 is 0. But second, 3 plus 2 times 0 is 3, works. 5, right? 1 plus 2 times 2 is 1 plus 4 is 5, so that works. That means this is the row operation that you apply onto A to get B in this step. That means E here is gonna be, so row 3 will be changing, so that means the first row and the second row stay the same, and the third row will be row 3 plus 2 row 2. So 0 plus 0 is 0. 0 plus 2, right? And then 1 times plus 2 times 0, which is 1. So this is the elementary matrix E, that when you multiply E to A, you get B. All right. Well, go to the next example. So next example, you want to find elementary matrix E such that A times E equals to B. In this time, keep in mind that if you multiply an elementary matrix 2 on the right of a matrix, that means you are changing the columns, one of the columns of matrix A. So we have to look at columns. So the first columns are not the same. The second column is the same, or the third column is the same. That means the first column has been changed. How does it change? So you see, there's an option is column 1, right? Is 4. It's changed from 4 to 2, right? So you can see that one possible way is column 1 equals to 2 times column 3 minus, right, column 1. That's one possible way. Because 2 times 3 is 6 minus 4 is 2. Okay. How about 2 times 2 is 4. 4 minus negative 2 is not negative 1. So this doesn't work. So if this doesn't work, then I have to find a different row operations. What is the difference? And what is another one? So another one can be column 1 equals to column 1 plus column 2. Does it work? So column 1 plus column 2. Because column 1 is 4 plus negative 2 is 2. Now it's negative 2 plus 4 is negative 1. Now, negative 2 plus 4 should be 2. So this row operation also doesn't work. How about the next? What is other possibility that you can come up with? How about column 1 divided by 2? Okay. So 4 divided by 2 is 2, negative 2 divided by 2, negative 1, 6 divided by 2 is 3. So this operation works for all the entries. That means from this row operation here, I can come up with the elementary matrix E, right? And again, you take 0, 0, and then the second column and the third column should stay the same. All right, this is how you find row elementary matrix to represent or to replace for row operations. Just keep in mind, instead of doing row operation, doing like arithmetics, right? You can come up with, you know, what row operation you want to do, then you can come up with elementary matrices that representing for those row operations. So then you can go from one matrix to its one of its equivalent matrices. All right, well, let's look at example number 12. So let A is this matrix and B is this matrix. Use elementary matrices to show that A and B are row equivalent. So by the definitions, in order to show that A and B are row equivalent, you need to find, to show this, you need to find a finite sequence of E1, E2 to EKs, right? Such that B equals to EK, E2, E1 times A. Well, that's the definitions. Well, then look at that definitions. Can we find the series of these elementary matrices? First, let's do some observations from A and B, okay? So from A, first row and the row 1 of A and row 1 of B are the same, but row 2 of A and row 3 of A are different compared to row 2 and row 3 of B. So to change from this row 2 to this row 2, what row operation that we can do is say this is 0. That means you can take row 3, row 2, right? Row 2 plus row 1, right? Because -1 plus 1 is 0. 0 plus 2 is 2. 1 plus 4 is 5. So that works. So this is the row operation that you are applying on row 2 to get this row 2. How about row 3? 1, 1, 2, 0, -1, -2. Again, the first entry is 0. So you can take row 2, 3 equals to row 2, 3 plus row 2. Well, I can guess that, right? And now I can see. If I take row 3 plus row 2, is going to be 1 minus 1 is 0. Works. 1 plus 1 is 1. Oh, this is -2 and 1, so it doesn't work. This row operation is not correct. Well, the next option is you take row 3 minus row 1. Okay, 1 minus 1 is 0. 1 minus 2 is -1. 2 minus 4 is -2. This row operation works for the third row. All right, so that means from this row operations, R2 plus R1, we can come up with E1 equals to, well, R1 and R3 stays the same. Just R2 is changing and R2 add to R1. And again, we want to look at the elementary matrices. I always want to have an elementary matrix, an identity matrix here, so then it's easier for me to do row operations on this matrix. So 1 and 3 is the same. R2 plus R1, 0 plus 1 is 1. 1 and 0. Okay, so for the row operation that applies on row 3, so row 3 minus row 1, then my elementary matrix would be row 1 and row 2 stay the same. And row 3 will be row 3 minus row 1. So 0 minus 1 is -1. 0 minus 0 is 0. 1 minus 0 is 1. All right, so I found 2 elementary matrices such that when I multiply each of this matrix to the left of A, I will get B, because I found the 2 row operation that I go from A to B. So I just show that A and B are row equivalent. And again, if you look at this 2 row operation, this 2 row operation are operated independently, right? So that means if you take, because I use row 1 to change row 2, and also I use row 1 to change row 3, that means I can do these 2 row operations independently and regardless the order. So I can do either multiply, use the E1, I multiply E1 to A first and then E2 to E1A, or I can multiply E2 to A and then E1 to E2 and A. Because then once I change row 2, so if I change row 2 first, then I have a new matrix, right? And my new matrix will be the same row 1, the new row 2, and the same row 3. And then I use row 1 to change row 3. So then that means my new matrix will be the same row 1, new row 2, and new row 3. So it's being said, because these two operations here are running independently, then B can be either E2, E1A, or E1, E2A. Will give you the same answer. So for number 13 is a proof problem. You want to show that if A and B are square matrices, n by n, and C is a product of A and B. So you want to prove that if B is singular, then C must be singular. So let's try to do this proof using the direct proof technique. So direct proof techniques just mean I assume that B is singular, right? And then I want to show that C must be singular. So assume that B is singular. It implies that the system AX plus B equals to 0. The system Bx equals to 0. So B is an n by n matrix, and Bx is a system, right? And Bx equals to 0 is a homogeneous system. And as you remember, that homogeneous system is always consistent because x equals to 0 can always be one of the solutions. But since B is singular, then Bx equals to 0, the system here will have a non-trivial solutions. Non-trivial solutions mean solutions that are not 0. Okay, and the reason is B is singular. So because B is, remember, if B is singular, then the inverse of B doesn't exist. If the inverse of B doesn't exist, then the system here has to have infinite many solutions. Okay, that means B of x has non-trivial solutions. Well, that implies that if you multiply A to B, so the system AB x equals to 0 also, right, has non-trivial solutions. I mean, it has many, many solutions. Well, what is AX? Because you can just multiply A to B and you have A to 0. A times 0 to 0. So this is why the system AX AB times X equals to 0 has non-trivial solutions. Third, because AX, A times B equals to C. Third, the system AC equals to 0 also has non-trivial solution. Therefore, C is singular. Okay. So again, using direct proof means you assume that A is singular and then you try to show that C is also singular. And since B is singular again, that means the inverse of B doesn't exist, right? That means if you take the system AX equals to 0, the system here by itself is already consistent because it's a homogeneous system. It always has a trivial solution, which is 0. 0 is always solutions here. But because B and B inverse doesn't exist, then B cannot reduce to an element non-trivial solution. Then if you multiply A to B, right, and A here, then the system ABX also has non-trivial solutions, okay, because these two systems here are equivalent system, okay, and because A times B equals to C by the assumptions that we have, then the system CX equal to 0 has non-trivial solution. Because the system has a non-trivial solution, then C has to be singular. This is how you use direct proof. The technique is called direct proof in order to show that if these are conditions, then if B is a singular matrix, then C has to be a singular matrix.